So what's it going to look like if we try to solve a system of linear equations that has three variables? Like this one. Well, you can see this system is still linear. Each variable only shows up times a constant, never times another variable, and only shows up to the first power. What could we do to solve this kind of system? Well, for this system, the goal is to find a single x, y, and z that satisfy all three equations. Well, this looks a lot like the two-equation, two-variable system. It's just that it's a little bigger, so we could try the same tricks. We could do substitution. We could solve one of these equations for one of the variables and then plug that into the other equations. And we could also try elimination. We could try adding multiples of equations to other equations to get variables to cancel. So let's try substitution first. So to do substitution, we need to solve one of these equations for one of the variables. Why don't we solve the third equation for x? That seems like a reasonable way to do it. So we're going to get x is minus y plus 3z minus 4. And now we need to plug that into the other equations, and we actually need to plug it into both other equations. Okay, so when we do that, we get minus x, which is minus y, plus 3z minus 4. So that's just the x part right here. So now we need 3y plus 2z equals 4. And then for the second equation, minus x again, so minus y plus 3z minus 4 plus 2y plus 4z equals 3. Okay, now each of these equations we can simplify. So it looks like we have a minus minus y, so there's plus y minus 3y, so that's minus 2y. And then minus 3z minus 3z plus 2z, so that's minus z. And then on the left-hand side, we have a minus minus 4, so that's plus 4. So when we subtract 4 from both sides, we get a 0. And now for the second equation, we have a plus y plus another 2y, that's 3y. And then minus 3z plus 4z, that's plus z. And then plus 4, and when we subtract 4 from both sides, we're going to get a minus 1. All right. You can see that when we do substitution to eliminate x in this way, what we get is a smaller system of equations with fewer variables. So now we're in the 2 by 2 situation. So, again, we can choose substitution or elimination. I guess we're doing substitution, so let's stick with substitution. Let's take this first equation and solve it for z. That's going to be easiest just because we can move z to the other side. We get z equals minus 2y. And now we can plug that into this last equation. We get 3y plus z, which is minus 2y, equals minus 1. And this tells us that y is minus 1. Now that we know y, we can turn around and find z. Right? Over here we know that z is negative 2y. So negative 2 times y, but y is minus 1, so that's 2. So y is minus 1, z is 2. And now we can go all the way back up to this equation and use y and z to find x. So x is negative y, which is minus 1, plus 3z, which is 2, minus 4. So plus 1 plus 6, so that's plus 7, minus 4 is 3. So our x, y, and z are 3, minus 1, and 2. All right. Well, that seemed to work okay. You can see it was a fair amount more work than a two-variable system, but that's to be expected because, after all, there are more variables lying around. Let's see how this system of equation works out when we use the elimination idea. So remember, the way of solving using elimination is to multiply equations by constants and then add equations together to get variables to eliminate. And there's actually a sort of a shortcut way of doing that, which is we can do those two things at once just by adding a multiple of some equation to another equation. So what we can do is we can actually do several operations sort of all at once. So we can add -1 times the first equation to the second equation. So the first equation we're going to leave alone. So minus x minus 3y plus 2z equals 4. So now we can add -1 times the first equation to the second equation. I'm choosing to do that because it will make this minus x in the second equation disappear. So I'm eliminating this x from the second equation. So let's see, minus x in the second equation minus negative x, so that's no x's, and then 2y plus 3y, so that's 5y, and then 4z minus 2z, that's plus 2z, and then on the right hand side 3 minus 4 is minus 1. Okay, now at the same time I can add 1 times the first equation to the last equation, because that will also eliminate an x in this last equation. So minus x plus x, that's no x's, minus 3y plus y, that's minus 2y, and then 2z minus 3z, that's minus z, and then on the right hand side 4 plus negative 4, that's 0. All right, now looking at just the second two equations, you can see that we've eliminated an x just in the second two equations. So what we can do now is work just with the second two equations and do the elimination method on them. The first equation is just kind of coming along for the ride. So let's see, to make progress on elimination, let's see, maybe the easiest way to do it would be, why don't we add 2 times the last equation to this middle equation, because that's going to get these z's to eliminate. Okay. Actually, let's not do that. We could do that. That would be fine, but there's actually a trick that I want to show you. So let's eliminate some y's. So let's multiply the second equation by 2 and the third equation by 5. So I'm doing that to make it so that these y's have the same coefficient, or at least the same magnitude of coefficients. So first equation is still minus x minus 3y plus 2z equals 4. Second equation is now 10y plus 4z equals minus 2. And third equation is now minus 10y minus 5z equals 0. Okay. Now we can use this y term in the second equation to get rid of the y below it. You can see what we're doing is we're sort of, every time we have a variable in the upper left corner, like this x here, we're using it to zero out the stuff below it, right? Once we've done that, then we take the new variable in the upper left corner, or a new term in the upper left corner, ignoring that first equation, and we're using that to zero out the terms below it, right? Okay, so minus x minus 3y plus 2z equals 4. Second equation we're leaving alone. It's 10y plus 4z equals minus 2. And now we're adding the second equation to the third equation. That gets rid of all of the y's. So now we have minus z equals minus 2. All right. Now at this point, we have this sort of staircase pattern, right? And this is really what we're looking for. When you have this sort of staircase pattern in your system of equations, you're set up to finish solving in a really straightforward way. If you look at this last equation, that tells us that z is 2. Now that we know z, we can use the second equation because we can plug in our value for z. So we get 10y plus 4z, but z is 2, equals -2. And so this is 8. Move the 8 to the other side. We get 10y is -10. And this tells us that y is -1. And now that we know z and y, we can substitute that back into the first equation. So then we get -x minus 3 times y, which is -1, plus 2 times z, which is 2, equals 4. And then, so this gives us -x is, let's see, there's +3 plus 4. Yeah. +3 plus, yes, +7 equals 4. So -x is -3, so x is 3. So for x, y, z, we get 3, where's y? There it is, -1, 2. Okay. There are actually several tricks that you can use to make this elimination process more efficient. One of them is at this point here, I could have added 2 times the last equation to the second equation, and that would have used this -z to zero out the z above it. Right? So in general, you want to aim for this stair-step pattern, but you don't always have to. As long as you're using terms to zero out terms above and below them, you're still making progress. So there's sometimes some tricks that you can do to make things a little shorter. This process of using the last equation to find a value and then substituting that into the equation above it and then using those to go to the equation above it, that's called back substitution. And once you have this staircase pattern to your variables, you're ready to do this back substitution to get all the values for the previous variables. All right. So you can see that I did a lot of writing I didn't need to do, really, like copying down this first equation several times. If you only do the writing you really need to do, elimination usually turns out to be a faster way of solving than substitution. At least that's my experience. So in general, right, we have this procedure for solving a system of linear equations. First of all, move all of the variables, all of the terms with variables in them to one side, and all of the terms only with constants to the other side. So we didn't have to do that on this example because it already started out, set up that way. But right, you can see all of the terms with variables are on the left side and all of the constant terms are on the right side. So once you've done that, use the far left term in the first equation to zero out the terms below it, and then use the far left term in the second equation to zero out the terms below that, and go on, and so on. So repeat until you have that stair-step pattern, and then back substitute to find values for all of the variables in your equation.